All right, welcome everyone. So today we're going to continue on with lesson 32, which we didn't quite finish last time because it's a lot of dense material and it's a long lesson in addition to that. Um, but yeah, so let's just go ahead and continue where we left off last time. So what we were doing last time was we were computing things called surface integrals. So these were sort of the next dimensional version of a line integral. So rather than following a line through three-dimensional space, we're instead kind of going over a parametrized surface, and we're integrating over that. And remember, the way to think about these integrals, which are also called flux integrals, is if we have some kind of surface floating here, so here's our surface, and we have a vector field in space, then we're effectively computing how much the arrows are piercing through our surface. And if they're piercing through in the same direction as the surface's normal vector, that will contribute positively. If they're going in the opposite direction, that will contribute negatively, like if they're going into the surface. And then it'll be zero if they're moving tangential. So it's effectively what we're computing here is how much these arrows are poking out of the surface. That ends up having a bunch of physical applications, some of which we'll end up seeing today. All right, so anyways, let's go ahead and start computing these. We already started last time with an example, so let's do another example. Evaluate the flux integral f dot n ds, where f is this vector field, x, y, 4x squared, y, z. And the surface is given by z is x e to the y right here. Now, this is good because we have our surface as z is a function of x and y. So we already know a specific form for flux integrals in that case. Now, x is limited from 0 to 1, and so is y. And we need to make sure that when we pick our normal vector here, the surface is oriented so that the z component of the normal vector is positive. That's what we're defining to be a positive orientation. All right, so let's go ahead and compute our normal vector here and make sure it agrees with this orientation. So if you recall from last class, we had a special formula for the normal vector to surfaces given by a function of x and y. This was negative partial g partial x, negative partial g partial y, and 1. So already we see that our z component will be positive because our z component will be 1. So we don't need to do anything to change this. Like we don't need to multiply by a negative sign or anything like that. All right, so let's see here. So what is this going to be? Well, negative g negative, or partial g partial x will be negative e to the y. We have the negative of the y derivative, which will be negative x e to the y, and then we have 1, no matter what. All right, so now we're ready to do our vector field here. Now remember, we usually want a parameterization of our surface, but in this case, since we have z as a function of x and y, we're just going to do this as x is the x coordinate, y is the y coordinate, and then this function, x e to the y is our z. This is kind of like our basic parameterization if we already have our surface function. All right, so now let's go ahead and do the integral. So the surface integral, or the flux of f dot n ds, well, let's see here. So our f, our vector field here, is going to be x, y, 4x squared, and then y times z. So we have x, y, 4x squared, and then y. Now, the thing is, we're not writing z as z right here. We're writing z as x e to the y because z equals x e to the y. So we have y, and then we have x e to the y for that. Why just x and y? We want to, for every surface we have, we want to try to represent it with just two variables. So we're choosing x and y to be our two variables here. And we're able to do that according to this one. And then we go ahead and dot this with negative e to the y, negative x e to the y, and 1. And then since we're using our parameters now, we can go ahead and just write this right here, y and x, and both of those went from 0 to 1, according to the problem here. X goes from 0 to 1, y goes from 0. All right. Why is the z component different? Because we want to write z in terms of x and y. Remember, we want to have two and only two variables for our surface. So we already know z in terms of x and y, so we're going to write it like that. All right. Also, I like Sam's description here. It's a simplified version of reparameterizing everything with u and v. It's like your u is x and your v is y. So it's kind of like the easy parameterization. Why is it yx e to the y here? Because it's y times z, and z is x e to the y. All right. So let's do this here. 0 to 1, 0 to 1. We have xy times negative e to the y, so negative xy e to the y. We have 4x squared and then this, so that's minus 4x cubed e to the y. And then we have yx e to the y times this. All right, and there we go. Now this is actually pretty nice because this and this will cancel out. So we're just doing the integral of negative 4x cubed e to the y right here. Now this is especially nice because we have all constant bounds for our integral. So we could just split this up over multiplication. So we do the integral from 0 to 1 of negative 4x cubed dx, and the integral from 0 to 1 of e to the y dy. All right, so then we go ahead and integrate here. We raise x cubed to be x to the fourth and divide by 4. That's from 0 to 1. Integral of e to the y is just e to the y. And then this ends up being negative 1, and this ends up being e minus 1. So we end up getting 1 minus e for our flux right here. Where does the r of t come in? We substituted in our parameterization in for the vector field, although it didn't really look like it because it was already in terms of x and y. The only real difference was that we substituted in x e to the y in for that z right here. We don't calculate RU cross RV. This is RU cross RV right here. This is RU cross RV if you use this particular parameterization where you just have x is the x coordinate, y is the y coordinate, and then your function is your z coordinate. Does this represent the rate of change of something over a membrane? It represents how much your arrows are piercing through your membrane. So this is actually a negative number, so it seems like our arrows are more pointing in towards the membrane rather than piercing out. No, these are multiplied together. It's negative 1 times e minus 1. All right, I'm sorry, guys. We got to get going here because we have a lot of stuff to cover. All right. So finally, we get to see a physical application here. So the heat flow vector field for conducting objects is the force field is negative k times the gradient of t, where t of x, y, z is the temperature in the object at the given location, and k is some positive constant. Calculate the outward flux of the heat across the unit sphere if your temperature function is this right here. All right, so what this is saying is that if you have some kind of object with heat, it's going to radiate its heat outwards. So what we're going to do is we're going to see how much heat it's radiating outwards here. All right, so remember, we actually already have a parameterization for the unit sphere. So they gave it to us right here. And they already told us what r phi cross r theta is. So we effectively just saved some time right here. All right, so now what we need to do is we need to make sure that this is pointing the right way. So remember, I think we talked about this last class, whenever we have a closed object, like a sphere, like that's enclosing a volume, the normal vector in the positive orientation is pointing outwards, away from the sphere. So what we want to do is we need to make sure that our normal vectors are pointing outwards. So what I mean is, here's our coordinates. Here's our sphere right here. We need to make sure that, for example, the normal vector right here is pointing this way and not into the sphere. All right, so the way we could do that is we could just plug in this specific value and see if it's pointing the right way. So, for example, if we're going along the x-axis, that has theta is 0 and phi is pi over 2. So let's go ahead and plug that in here and see if we get the vector 1, 0, 0, which will be pointing this way here. All right, so r phi cross r theta, which remember is our normal vector at this point, Let's see, sine of pi over 2 is 1, and cosine of 0 is 0, so this is 1. We have sine of pi over 2, which is 1, sine of 0 is 0, and then cosine of pi over 2 is 0. All right, so this parameterization here gives the orientation the right way. Because technically going inwards in this direction would have also been a normal vector, but that's not really the one we want. We want things pointing out from the surface. All right, so now we know that this is oriented positively, so that's good. So now we need to figure out what our vector field looks like here. So f is negative k times the gradient of t right here. And they told us that t is the negative logarithm of all this. All right, so let's see here. Let's go ahead and compute the gradient of this. Well, let's see. If I take the x derivative of this, for example, I'm going to have 1 over, well, negative 1 over x squared plus y squared plus z squared. And then I multiply by the x derivative here, which is going to be 2x right here. Now, the thing is that all of this function right here is going to be symmetric. So x plays the same role that y does, which plays the same role that z does here. Yeah, this is going to be negative 2y, x squared plus y squared plus z squared, and it's going to be negative 2z. Yeah, Ryan, what's your question? Okay, well, I'm sorry, I gotta get moving here. All right, so let's see. I'm going to factor out all the x squared plus y squared plus z squared from all of this here. And then I'm going to factor out the negative 2 as well. So pulling out the negative 2. Wait, did Ryan actually say something and I just didn't hear it? I didn't actually hear anything.
No, he didn't say anything.
Okay, all right. I just wanted to make sure like my volume was on. Okay. Oh, it's a accident. All right. All right. Anyways, so I'm gonna pull negative 2 out and all of these squares here. So we have 2k over x squared plus y squared plus z squared, because that's in all of these. And then we have x, y, and z left over. All right, so this is going to be our vector field right here. All right, so now what we're going to do is we're going to do the surface integral of f dot n ds. All right, so let's see. So we're going all around the sphere, right? So we're going all around the sphere. So the sphere goes from phi is 0 to pi. So we have that. And then the sphere also goes from theta is 0 to 2 pi. So we're going to have that here. And then we have f, which will be 2k x squared plus y squared plus z squared. Then we have x, y, and z dotted with r phi cross r theta right here. Now, don't worry, I'm going to get these to match up with their coordinates in a second. So we have all the same variable. Sine of theta, and then sine of phi, cosine of phi, and this will be d phi, d theta. All right. Why are the bounds constant not in terms of other variables? Because it's just the sphere. That's why. The sphere just goes from phi is 0 to pi, theta is 0 to 2 pi. All right, half a page is too small for this problem. That's exactly why Dr. Huang's kind enough to provide us with another page here. All right, so let's go ahead and simplify this because this looks really ugly. X squared plus y squared plus z squared. There's a very easy way of writing that if we're on the unit sphere. What is this? Well, it's rho squared. That's true, but in this case, it's a sphere of radius 1, so rho squared will be 1. So you're all right. So this is going to be 1. So we have just 2k. And then x, y, and z, we actually have parameterizations for those. It's sine of phi, cosine of theta, sine of phi, sine of theta, and then cosine of phi. And then I'm going to do dot, and then I'm just going to write r phi cross r theta, so we don't have to write the thing again. R theta. All right. Okay, and then now we're going to take the dot product of this and this, and we're going to get something that initially seems really nasty, but it's going to simplify into something that's not too bad. So let's see, I have this 2k here, and then I have sine of phi cosine of theta dotted with this right here. Remember, this is the first component of that. So we have sine cubed of phi cosine squared of theta. That's this dot this. Then we have sine of phi sine of theta dot sine squared of phi sine of theta. So this is again going to produce a sine cubed of phi, and then we have sine squared of theta right here. And then finally, we have cosine of phi dotted with this. So this will just be plus sine of phi cosine squared of phi. And then we have d phi. All right, now this looks awful. This looks like definitely something we don't want to integrate, but there are definitely going to be some simplifications here. The first thing is that we see a sine squared cosine squared pair. So this will reduce to sine cubed of phi, because that's the coefficient for both of them. Now look at this. I have sine cubed of phi. Another way of writing that is sine of phi times sine squared of phi, right? That's sine cubed of phi. Now, if I look here, writing it this way gives me another sine squared cosine squared pair. So I have cosine squared sine squared, and this time the coefficient is just sine of phi. So all of that was just a fancy way of writing sine of phi. 2k sine of phi. We have d phi, d theta right here. All right, and then now we just need to do this integral, which again, we can use the multiplication rule. So this is the integral 0 to pi, sine of phi, d phi, integral 0 to 2 pi, d theta. I'm going to kind of speed through little things like this because I definitely want to have time to get to the important stuff here. So this is just going to be 2k, this integral will be 2, and then this one will be 2 pi. So we end up with 8k pi. So that's going to be our heat flux going through this sphere. And it makes sense we get a positive answer because we have a hot object in here and then cool ambient air out here, the heat's going to radiate outwards. So if we drew a sphere around it, the heat is definitely coming out of that sphere. So this is greater than 0 here. All right, now there's actually a sneaky way to do this. So the trig stuff was a little bit sneaky, but there's actually another way we could have done this problem. Let's take a look at this here. Why is it 8 not 4? 2 times 2 times 2 times k times pi right here. A quick way to compute this, the gradient of t is always parallel to the position vector. Remember, we were able to write it as 2k over x squared plus y squared plus z squared times x, y, z. So it's parallel to the position vector. So at the surface, at the unit sphere, this is always going to be normal to the surface, because if we draw our sphere, so here's our sphere again, if we draw a position vector pointing to a point on the surface, notice that this vector here, this little arrow, is parallel to the normal vector that we would have here. So this will also be normal to the surface. And then we can see furthermore that the magnitude of f will always be 2k. So if we compute the magnitude of this vector, we're always going to end up getting 2k from this. I'm not going to go through the calculations. We just end up getting 2k here. All right, so the magnitude of f is 2k. And then what we do is we multiply by the area of the unit sphere, which is 4 pi r squared, or 4 pi times 1. So we just get 4 pi right here. And then multiplying by the 2k magnitude gives us 8 pi k. So what this is saying is that per unit area of the sphere, each per unit area of the sphere is radiating 2k of heat. And there are 4 pi units of this area, so you get 8 pi k. That's just kind of a sneaky way of doing this. Don't worry if you didn't see it that way. Doing it the other way wasn't too bad either with the rest of with the way we did it earlier. All right, let's do one more application here. And this one will also kind of have a sneaky way of doing it if we kind of imagine things visually here. All right, so suppose F is the vector field 0, 0, Z, and it's the vector field of a fluid flow. So that's another thing these vector fields can represent. So it's the rate of fluid flow in R3. Calculate the flow rate in cubic meters per second out of the closed cylinder, x squared plus y squared equals 1, and the height ranges from 0 to 1, including the top and bottom discs right here. All right, so let's draw this. So we have our unit circle, x squared plus y squared is 1, and then this extends upward a height of 1 here. So we end up getting this, this cylinder. Oh, my top circle looks smaller than this, but whatever. Here's our cylinder. All right, so what we're doing is we have this vector field, and well, actually, I do know how this vector field is going to look. It's just 0, 0, Z. So the further up in Z we are, the more our arrows will point up. So we have bigger upward arrows here, and then we have 0 vectors actually down on the bottom here. So this is what our fluid flow looks like, and we want to calculate the net amount of fluid that's coming out of our cylinder. So it definitely seems like some fluid's coming out of our cylinder. It actually looks like it's mostly coming out of the top here, according to this picture. But let's go ahead and do a surface integral to know for sure. All right, so I'm going to draw this again. So if it's a surface integral, we got to be familiar. Oh God, we got to be familiar with all of the different surfaces here. So we can divide a cylinder into 3 parts. We have the bottom of the cylinder, the base, which I'm going to call S1. We have the top of the cylinder, which I'm going to call S2, and it's said to include the top and bottom here. And then the side will be S3. So what we're going to do is we're going to compute the flux over each one of these surfaces separately. So we're going to do F dot ds over each one of these separately. So this will be the flux over the first surface plus the flux over the second part of the surface, the top, and then we have the flux out the side. All right, so we're just going to compute each of those separately here. All right, so let's do S1 here. Now, S1, this surface is just the surface where we have Z equals 0, and x squared plus y squared is less than or equal to 1 right here. All right, so let's see here. So technically we have our surface. If we want to pick a normal vector for this surface, remember, we always want the normal vector pointing away from the interior volume. So for S1, we want our normal vector to look like this. So if we want this to be a unit vector, we want this to be n hat. What is this normal vector going to be? What am I going to make this normal vector be? It's pointing directly down, and it needs to be a unit vector. 0, 0, negative 1. Absolutely right. Bingo. All right. We got 0, 0, negative 1 here. That's going to be our normal vector. All right, and then let's take a look at our vector field. So our vector field, according to the formula, always has 0 and 0 for our first 2 coordinates here, and then it has z for the last coordinate. But in this context, if we're on the bottom here, this is z equals 0. So we have the 0 vector field. How did I know this? I just needed a unit normal vector to something that's flat on the xy plane, that's pointing down. So those requirements kind of force me to pick 0, 0, negative 1. All right, so I know my normal vector, I know my f. So this means that S1 will be 0, 0, 0 dot 0, 0, negative 1. And I don't even need to worry about what area this is, like what my variables are here, because I'm just going to be doing the integral of 0. There's a big old 0 if I do that dot product. So this is going to be 0. So there's actually no fluid or no net fluid flow through the bottom of the tube. So nothing's coming out the bottom of this tube here. All right. So that's S1. There's no contribution from that. All right, so let's see if there's any contribution from S2. S2 is the same thing, only this time Z equals 1 right here. So Z equals 1. We have x squared plus y squared less than or equal to 1. All right. So let's see here. Let's come up with our normal vector. All right. So this will be very similar to what we did for S1 here. We want a normal vector so this is totally flat. It's parallel to the xy plane. And we want a unit vector that points away from my volume here, so it's going to be pointing up. So what's that going to be? And yeah, you guys preemptively knew what it was. Our normal vector for S2 will be 0, 0, 1, because again, it's pointing away from the interior volume. 0, 0, 1. And then now let's take a look at our vector field here. It's always 0, 0, z. But in this case, z equals 1. So our force field is 0, 0, 1. Our vector field is 0, 0, 1. All right, now if we do this double integral, S2, we have 0, 0, 1 dot 0, 0, 1. Yeah, that's fine. So 0 times 0, 0 times 0, 1 times 1. So we're just doing the integral of 1 ds right here. So that's all we need to do for this. Now remember, the integral for 1 ds, that has special meaning, right? The integral of 1 is just the surface area of S2. So it's just how much area S2 has. But the thing is, S2 is just a circle of radius 1, right? So the area is going to just be pi r squared. And since it's radius 1, it's just going to be pi. So this integral is just pi. We didn't actually need to do anything to compute that. We just end up getting pi for this one. So out of the top of it, there's a net flow outwards over the top of pi cubic, I think it's meter or cubic meters per second. All right here. How would you set the bounds? You could just use polar coordinates for this if you want. So you could parameterize it that way. So you can use r and theta 1. Why not 2 pi? Because the area of a circle of radius 1 is just pi. It's not the circumference, it's the area. All right. And now we actually have one more surface to deal with, and thankfully we have more paper to do that with. Our last surface is S3. So S3 is where x squared plus y squared equals 1, and z is the thing that can vary now. Z can go from 0 to 1 right here. Okay, so this one's going to take a little bit more thought than the other ones. So I'm going to parameterize this. I'm going to parameterize it in terms of theta and z. So I have an idea, since I want x and y to be kind of in the unit circle here. I'm going to have x is cosine of theta, y is sine of theta. Ooh, Sam has a good idea here. Hold on to that, yeah. And then z is z. This is going to be my r theta z right here. All right, and then let's compute r theta and r z. Our theta is negative sine of theta, and then take the theta derivative of this, take the theta derivative of this. Meanwhile, our z will be 0, 0, 1. Now we need to do r theta cross r z. Okay, let's see, we have I, j, and k right here. And then we have negative sine of theta, cosine theta, and 0, 0, 0, 1. All right. So let's see here. So we have we have cosine times 1 minus 0 is cosine. We have j, we have negative sine times 1 is negative sine, but then it's the j, so we get rid of the negative. And then with k, we have this times 0, this times 0, which is 0. Okay, so our r theta cross r z is this. Now, if you look at this, this is just a parameterization of the unit circle. So if we draw our cylinder one more time, we need to make sure this is positively oriented, right? So we want our arrows pointing out, away from here. But if we have them pointing in the direction of the unit circle, like if we plug in theta equals 0, we're going to have the coordinate 1, 0, 0, which is like this. So it does seem like all of our vectors will be pointing away from the cylinder here. If we don't make this little check right here, we run the risk of being off by a negative slope. All right, so we have that. And then now our force field, F, I keep calling it a force field. It's just a general vector field. I don't even think it's a force in this context. F is 0, 0, Z. And we can just keep it as Z because we've parameterized it that way. All right, so now we have everything ready to assemble our surface integral right here. So we have S, and then we have F dot R theta cross RZ, which is our normal vector, the A. I guess this should be D if I'm using the parameters. Now, what's this dot product going to be? So this is 0, 0, Z dotted with cosine sine 0. So once again, this is actually another integral that we don't have to do anything with because we have 0 times this, 0 times this, and then Z times 0. This is yet another integral of 0. So we end up with 0 water net flow out of our cylinder right here. I think it was Sam that had the right idea the whole time. So if we have the total flux, it'll be 0 plus pi plus 0, which will be pi. Now, there's another way to compute this, and this one I think is a bit more intuitive than the previous way. If we draw the vector field again and then the cylinder, remember that our vector field was just 0, 0, Z, right? So it's going to be 0 vectors down here, which I'll represent by just little points. We have tiny vectors here. We have medium vectors here, and then we're starting to get some bigger vectors as we come out here. And remember, the normal vectors are going to be like this, and like this. So on the bottom, our force field is 0. So there's no flux happening in either direction here. So this is going to contribute 0 right here. The top, we have the normal vector pointing up and the vector field pointing up as well. So this will contribute positively. And then along the sides here, we have these upward pointing vector field vectors, but those are all going to be perpendicular to these sideways pointing normal vectors here. So coming out of the side will be 0 as well. We have 0, 0, and then positive. And the magnitude of all of these vectors up here is 1. So we're just doing, like we just actually did, we're doing the integral of 1 ds, which is just the area right here. That's a way we can kind of intuitively do this, or at least see that our answer is correct. So this is water flow. So this is fluid flow, which can be represented by a vector field. How is fluid being creative? I have no idea. This is just the context of the problem. I have no idea what's actually happening physically. All right, and that's it for lesson 32 right here. So how are we doing on time here? I have a bad feeling. All right, well, we'll try to get some of this done here. So the next lesson is entitled Stoke's theorem. So this is going to be our next version of a fundamental theorem of calculus right here. This is going to be the next one we're going to counter after we already looked at Green's problem here. All right, so let's see. So speaking of Green's theorem, so we saw that we could use Green's theorem, but the vector fields we applied that to back then, they only had components P and Q. Because remember, well, I guess I'm gonna write this on another page. But for Green's theorem, we always did the double integral of Qx minus Py, where our vector field was just P for the X component, Q for the Y component. Right here. All right, but now let's say we end up with a vector field that's in 3 dimensions. I think someone literally asked this question on that day. Can we do this in 3 dimensions? And the answer is yes. So we're going to be able to generalize Green's theorem to vector fields that live in 3 dimensions, not just in the XY plane. That's what we're going to be doing for this lesson. Now, before we do that, we need to come into contact with a concept known as the curl of a vector field. And the name actually kind of fits this. So what is the curl of a vector field? Well, the curl of a vector field, if the components are P, Q, and R, and we need to make sure we can take the derivatives of these because this is going to involve partial derivatives here, then what is the curl? The curl is this seemingly mysterious formula where we have R sub y minus Q sub z, we have P sub z minus R sub x, and we have Q sub x minus P sub y. So this is going to be our curl right here. So this kind of seems random, you know, where on earth did we get these from? Although you may recognize these as, if we made these all equal signs, for example, this would imply it's going to be conservative. So it does seem to have that going on. But why are we subtracting these? Why are we doing it in this order? Why is this component here and not here? We don't know that yet. Now, there's a special name for a vector field with 0 curl. And remember, curl is a vector. So if you ever write that the curl is 0, we need to put the little vector thing. I'm guessing we have to memorize this formula too. To be entirely honest with you, I don't have this formula memorized. There's actually a way of doing this where you don't have to memorize it, which I'll explain on the next page. All right. So if the curl is the 0 vector, then F is called irrotational, meaning it's not curling. And the curl of a vector field is a vector field because it's a vector right here, and it'll be a function of x, y, and z. Okay, now I just claimed that there was a way we can get around memorizing this, and I'm all for not having to memorize stuff. I'm really bad at that. So how are we going to do that? Well, there's another way that we can compute the curl besides this formula, and it involves what's called the del operator. What on earth is the del operator? We may recognize this symbol for when we computed gradients before, and this does have something to do with the gradient. The del operator is a vector where we put the partial derivative for each component in its matching component. So we have the x derivative in the x component, the y derivative in the y component, and the z derivative in the z component right here. Now, you might be kind of wondering about this, like, oh, wait a minute, this is missing the function here. Why, like, how could we do that? It's kind of similar to in Calc 1, when we kind of just regarded d dx as something on its own that could be applied to something. The del operator is also something that could be applied to something. And it's almost like we just have a d dx in each one of the components. All right, so then it turns out that the curl actually has a nice formula in terms of this del operator. And I think someone predicted this earlier. It ends up being the cross product of these partial derivatives with f right here. All right, so let me show you what I mean on, well, actually, let me just show you what I mean in an example here. So we're going to take the gradient of the curl crossed with f. All right, let's take a look at an example. Calculate the curl of this vector field here. So this is the component P, this is Q, this is R. So in the process of doing this, I'm going to show you why that previous formula works. So we want to know the curl of F, which I claimed was the del operator crossed with F. All right, well, how do we do a cross product? Well, we have our determinant. We always have I, J, and K hat. And then we put the components of the first vector. Now, these are partial derivatives. And then we put our components of the second vector next, which I'm going to call P, Q, and R. All right, so what we're going to do when we do this determinant right here is we're going, every time we multiply a derivative by one of these functions, that's going to be taking that derivative of that function. So for example, let's compute I hat here. I hat is this times this minus this times this, right? So if I do this times this is going to be the y derivative of r. So I have r sub y, and then I subtract, and I have the z derivative of q. All right, we do the same thing for j. I have the r derivative of or I have the x derivative of r minus the z derivative of p. But remember, j flips things around right here. So I'm really going to do the z derivative of p first. So I flip the sign, and then I subtract the x derivative of r. This times this. And then finally with k hat, I have qx minus py right here. And there we go. So there is our formula that we had on the previous page. And to be entirely honest with you, I don't have this formula memorized. I kind of just go through this every single time here. Although if you're someone who likes to memorize things, you may save a little bit of time by memorizing this right here. What does this represent in a vector field? I'm going to get to that in a minute. All right, so let's go ahead and compute it for this. So the curl of our particular vector field here, let's see, I'm going to have r sub y, so that's going to be xz squared minus q sub z, so that's xy squared. All right, next I have pz, which is x squared y, minus rx, which is yz squared. Yeah, no, that's right, that's right. And then we have qx minus py here. So qx is y squared z. And then py is x squared z. All right, so this is going to be the curl of our vector field. And then notice that this itself is another vector field. So a vector field is a function of 3 variables that spits out a vector. This is also a function of 3 variables that spits out a vector right here. Okay, now Tristan just asked, I think it's Tristan, what does the curl actually represent? It has this particularly strange name, curl. What is that talking about? The curl of f measures the tendency for a vector field f to rotate about a given point. So that's what f measures here. So suppose we place a paddle wheel onto a vector field. The paddle wheel rotates the fastest when the axis of the wheel points the direction of curl of f at the given point. So if we look at this color, oh no. My thing unplugged, just a second. There we go, it has returned. Okay, so the curl of f, so notice how if we, let's take our fingers, right? So let's take our fingers and let's literally curl them in the direction of the vector field. So we do that, and then our thumb is pointing in the direction of the curl vector. So if your vector field has any kind of properties of spinning or rotation or anything like that, the curl will measure, the magnitude of the curl will measure how intense that spinning is, and then the direction of the curl will be the axis that you're going to be spinning around right here. So that's why it's literally called the curl, because you're measuring how much your vector field is curling around our certain point here. Does this relate to the
professor? Sorry to interrupt, but your mic it just got weird for some reason.
Oh, all right. Let me unplug it and plug it in. Okay, is that better?
No, I think the mic changed. I think it's just using the default inbuilt mic or something.
Oh my God. Okay, did it switch back to the way it was? All right, whatever. All right, so yeah, sorry. We only have 5 minutes left. Hopefully it'll get through here. All right, so that's what the curl is. It just represents how much your vector field is spinning around a particular point right here. All right, so let's talk about the curl of conservative vector fields. So this, so we've seen so far the conservative vector fields are really nice, right? Like there's 0 involved with them quite a bit. So maybe there's something nice here. Well, there is something nice here. If you take the curl of the gradient of a function, it's going to end up being 0 right here. So let's see why this is. So if we do the curl of the gradient of a function,
then this is going to be del cross the gradient of f here. So we have I, j, and k. We have partial x, partial y, and then we have partial z, and then we have partial f, partial x, partial f, partial y, partial f, partial z right here. All right, so let's go ahead and compute the components here. So if we look at the I hat right here, we have partial y times fz, so this will be fyz because we did a y derivative. And then we subtract, and then we do partial z of y. Okay, that's interesting. All right, and then if we do the j component, I'll just speed through this, make sure we have enough time. This will be fzx minus fxz. And then the k component will be fxy minus fyx right here. All right, now there's something very interesting about this vector field, particularly if we have continuous second partial derivatives. What is all of this going to be if we do the derivatives in the opposite order? Those are all 0. That's right, provided they're continuous, we don't have anything nasty going on. That's right, this is just going to be 0 because of the equivalence of mixed partials, or Clairaut's theorem, which we talked about earlier. So if we have equivalence of mixed partials, then the curl of our gradient will be 0. All right, now there's another way that we can think about this. I did this for a reason here. So if f is conservative, remember, if f is conservative, then there is a little f, a scalar valued function, such that the gradient of that is big F. This is a curve here. This is little f. All right. So then if we do the curl of f, which can be written this way, the curl of big F is the curl of the gradient of little f, but we just saw for any gradient, that will be 0. So if f is a conservative vector field, then it has no curl whatsoever. Can I show the upper part? Yeah, I was just doing the curl here, and then I was doing the equivalence of mixed partials right there. All right. Now, if the curl of f is equal to 0, does this imply that f is conservative? Well, let's think about that. Let's go back to our definition of curl here. Where did I put that? All right. So if the curl of f is 0, that means that each one of these is 0, right? That's what being the 0 vector is. So that means that ry will be qz, pz will be rx, and qx will be py right here. So in this case, remember, those were the 3 cross-partial conditions that if we were in a simply connected domain, and that was a big if, we saw what happened when we removed the origin, that was bad. But if we are simply connected, then having these conditions right here will guarantee that we are conservative right here. So unlike a lot of theorems in math that don't really go both ways, like the test for divergence back from Calc 2, it's probably the best example of something that doesn't go both ways. If the curl is 0, does this imply f is conservative? Yes, the answer is yes. So long as the domain is simply connected. All right. How much time do we have here? Are we done? I'll try to do a little more. Okay. Let me kind of just set up what we're going to do for next time. All right. So now we can finally, now that we know what the curl is, now we can get to the 3D version of Green's theorem. So where we have a vector field with 3 components here. All right, recall Green's theorem. So Green's theorem, we have the boundary of some domain being a smooth curve oriented clockwise or positively, and it encloses a simply connected, we have to have that, region D. Assuming that f is just p and q, so this is only in the xy plane, p and q have continuous first partial derivatives, then this is going to be the double integral over d of qx minus py dA. And we saw, I think it was in lesson 30, what we were able to do with that. All right. Now suppose that we modify the vector field f by considering it to be three-dimensional. So we're going to have p and q be as they were before, and then we're just going to regard the z being 0 because we're in the xy plane. So z will be 0 here. Then it turns out that the curl, and I'm just going to speed through this. If we go through the determinant and we compute the curl, it's going to be 0, 0, and then qx minus py right here. And this actually makes sense here, right? Because if there's any kind of curl going on in the plane, so we're curling, imagine my fingers are curling through the xy plane, my thumb is going to be pointing either in the z direction or the negative z direction. So my only component for my curl has to be z right here. All right, so that means that we can express this a little bit differently, and this is going to lead us into next class here. So I'm going to kind of leave us on a cliffhanger here. So this is going to be, f dot dr is going to be the curl of f dotted with k hat. Okay, now why is it k hat? Well, remember, k hat is just the unit vector for the z component, right? So we took the curl, which is all of this, and we don't even care what happens with these guys, so we don't need an I or a j hat. All we need is a k hat right here. And this is going to be our normal vector, because if we have the xy plane, like right here, what's a normal vector for that? It's just going to be k hat. It's just going to be going in that direction right here. Is that only when z equals 0? Yeah, we'll get to the full generality where we don't have z being 0 will be next class. But this is kind of showing you that what we learned in lesson 30 is a special case of what we're going to do next time, where we use the curl as a tool to evaluate these integrals right here. So next time we're going to be able to alter the formula a bit so we can have z being non-zero. All right, hopefully the sound wasn't too bad for that last bit right here. But anyways, I will see you guys on Wednesday where we will hopefully try to finish this lesson and then maybe begin lesson 34. All right, so let me stop recording here.